Good afternoon. I'm Bernadette Glover, and I'm the branch librarian here. It's my pleasure to introduce our guest speaker, Jared Head, who will present a program on the James Webb Space Telescope. Jared is a solar system ambassador for NASA Science Solar System Exploration. Jared grew up in Downey and had a childhood obsession with spacecraft. In his adult years, he left a theater arts program to join an aerospace program. I think usually it's the other way around. But anyway, currently he works for the Griffith Observatory and co-hosts a science podcast with one of the largest online audiences. In his spare time, he also builds high-powered rockets in his garage. Jared's specialty is presenting high concepts in an easy-to-understand terms, and he definitely has a passion for the subject he presents. I'm thrilled to have Jared with us today to present information on the James Webb Telescope. Please join me in giving Jared a warm welcome.
Always nice to kind of come down the street from where we're at to talk to everybody about some of the latest and greatest that we have. And that is most certainly the James Webb Space Telescope, which I'm sure many people in here have heard about, or you might have even followed its journey out into space, the sort of terrifying 30 days that it spent unfolding. We'll talk all about that during this, and we'll do a little quick sort of brief history of how we observe things in the sky. We'll talk a little bit about the James Webb Space Telescope itself, and then we'll also look at some of the latest images and results that we've been getting from there, including some that we just got this week as well that we've been able to grab. So should be a lot of fun working with that. So, looking out into the universe. It's something that we seem to be really good at and sort of like moderately obsessed at doing, looking out from the Earth to see what's all around us. And most of us think of telescopes when we're looking at things, but does anybody happen to know what would have been the first instrument that us humans used to look out into the night sky? Yeah, your eye, that's right. Yeah, that's right. Your eye, not my eye there, but some eye, looking down upon us maybe. But looking up, yeah, your eyes. That's how for thousands of years we looked out into the universe. That was it. That's as good as it got for most of us. And some of us, like me, ain't even got it good, right? So it could be a little difficult at times. So go ahead. If you guys could look at the person next to you real quick. Hopefully you know them, so you can kind of look at me right here if you'd like to. Great shirt, by the way. I love it. You'll notice, again, look at them. I'm telling y'all, look at them. Say hi, neighbor. Even if you don't know them, be like, what's up, neighbor? So look into their eyes, like deep into their eyes, right? Now, we can all see that there's an opening in those eyes, right? And what do we call that? The pupil, yeah. And if you would, please, show me with 2 fingers how big your neighbor's pupil is. So we're looking at maybe about like there. If it's here, we've got some problems. But if we're there, we're pretty good, right? Yeah. So that, for thousands of years, is how much light gathering capability we had. That was it. A couple millimeters across at best. But then we actually started to make these instruments. And does anybody know what they're called? Yeah, telescopes. That's right. But we had to start, right? We had to start with our eyes. So this is how our eyes see everything, right? So we've got a great image here. I really love this one because we've got the Pleiades right there, one of my favorite star clusters to look at through my telescopes. And then we've got Jupiter hanging out down and in there as well, and a little bit of Milky Way kind of going through the top of that right there. So very, very, very nice image with that there. But then, of course, telescopes, right? And usually the first person that we assign credit to aiming a telescope upwards as Galileo Galilei. So he looked at the moon, he looked at Jupiter, he looked at the phases of Venus, he published these things, and boy, did he get into a lot of trouble. So, and he was a little bit of a troublemaker during his time, as most good scientists are, right? But this is essentially what he was working with. Not exactly what I would call the greatest instrument ever, but at the same time, it might actually be one of the greatest telescopes ever, because this is really where the idea of science, peer-reviewed science that we do nowadays, the foundation for how we actually operate is from Galileo's studies that he did of the sky. So absolutely astounding that he did that. This is what he probably saw with Jupiter in terms of resolution. There are some cell phone cameras that actually have the capability to take images like this. So you may be at a Galileo level of ability to do astronomy with that. But a Galilean telescope is one that allows light to go through two different lenses. And those lenses aim the light, they take it, and they focus the light so that it comes down and it fits through your pupil. So that's essentially the way a telescope that you're going to look through works. We're focusing it on a specific area. So then it actually sort of tricks you into thinking that your pupil is as big as the aperture of your telescope, or the size relative of your telescope. So where I work at Griffith Observatory, we have a 12-inch telescope up there. So we trick your brain into thinking that your pupil is about this big, which would make an eyeball probably about the size of you. So that might be a problem for many of us. And there we are. There's our Zeiss that we have up at Griffith Observatory, which you can come look through for free. There's my one plug for the talk. All right. So, but the biggest telescopes in the world that we use are not that Galilean style, or what we would call refractors. So where they refract the light or bend it. Most of them are what we call reflectors. So they use mirrors to bounce the light with each, bounce the light through their body and then to an eyepiece, or in the case of the largest telescopes in the world, to a set of instruments that you then work with. So I do find it funny that we build these massive telescopes and then we don't put eyepieces on them because we're putting instruments in them. So it's pretty amusing to me. So this is one of the largest in the world, which is one of the twin Keck telescopes up on Mauna Kea in Hawaii. It's about 10 meters in size. So to give you an idea of how big that is, 10 meters, from this side to this side of the library here is, I would guess, is probably about 6 meters. So we really wouldn't be able to fit the mirror inside of this here. Really good way we like to say it. Our dome for our telescope at Griffith Observatory, the footprint of the outer circumference of the dome is just a little bit smaller than the main mirror here for this. So, I mean, like this big, it's about 33 feet across. For those of you who don't do metric with that there, for those more inclined with American units, imperial that there. But eventually we said, okay, we've done enough with these really big telescopes here on Earth, so now we're going to start launching them into space. And you probably know what this is. What is it? Yeah, this is Hubble. So in its glory from STS-125, our final servicing mission 13 years ago. And Hubble was not the first space telescope, but it's probably one of the most famous space telescopes, mostly because of its longevity and its ability to perform observations around the clock. So Hubble is constantly in use. Because that time is precious, because Hubble was a little expensive, a couple billion, right? So you want to make sure that you get your money's worth out of it. And Hubble was launched in 1990, and it had a flaw with its mirror that was roughly, and get this, 2 nanometers in size. But it was enough of a flaw that it completely ruined the images that we were getting from it. By the time we were ready to fly a mission to fix Hubble in late 1993, we'd actually developed software that had gotten Hubble to about ground-based observatory resolution. And a lot of that we use today for compression of data for your computers and other things like that. So in case you're wondering where things like that come from, every once in a while, We get a little something from Hubble like that. And Hubble gives us great images, right? And we go from that like dot in the sky of our eyes to that disk without really a lot of detail of Galileo's telescope to now we're here with Hubble looking at Jupiter just in an incredible amount of detail with its atmosphere here. We could see that there's multiple bands going up against each other and the great red spot rotating, and a great image of a shadow of one of Jupiter's 4 largest moons being cast across on the top of its cloud tops. And then a lot of people also know Hubble for its deep fields as well. Basically, they point Hubble at one spot in the sky, and we just keep it pointed there for a really long time. And we take in all of the light, all of the photons that we can. And then this is the kind of image that we get, where we see that we really aren't actually one galaxy, that we aren't just the single galaxy here in our universe, right? That there are innumerable galaxies. We almost cannot even conceive of the numbers of these galaxies. And also just knowing that in this particular part of the image that I have right here, there's only 2 stars in this image that are in our own Milky Way. Every other point of light is a galaxy itself, even those little dots that you see far away. So yeah, there's a lot of stuff out there, it turns out. So that's pretty wild. And with Hubble, we were able to take some amazing imagery, such as this, the well-known pillars of creation. I saw this at the Griffith Observatory Planetarium back in 1996, and it blew my mind looking at that because the operator said, "This is about the size of our solar system." And I just, I was like 8 and I couldn't comprehend that. So that was amazing. And we'll actually come back to this in a little bit as well, several times actually throughout the talk. But obviously the light that our eyes look at is a very narrow band of light. It definitely works very well for us. But in terms of wanting to see all of the other light that we have out in the universe, there's like a lot. You can choose whichever you'd like, right? So what would this look like if we were looking in a different form of light? What do you guys think? Yeah, it would definitely look a little bit different as well. But we would have to kind of figure that out a little bit later because Hubble would need upgrades in order to do things like that, right? So, and that was the nice thing about Hubble. It was designed to be upgraded. So we were able to add on new instruments, pull out the old ones, work on that. Some nice things from Hubble that we were able to do. We actually brought material that had been in space for over 20 years back home and see what it does. So that's good. So it wasn't just astronomy. There's a lot of engineering that we learned from Hubble too. And this is actually an image of one of the furthest galaxies away that Hubble has seen, somewhere on the order of about 13 billion light years away from us. So this is essentially a galactic infant there, just a very tenuous mass of stars and gas and dust in an area there. And we'll come back to this in a little bit because Webb has possibly already exceeded this just in the first picture it took. So just some of the things that we like to talk about, of course, when we're working with Hubble. Probably my favorite one is LASIK. So the systems that were used to align the light coming from the deformed mirror ended up being used to develop new algorithms and systems that enhanced LASIK somewhere on the order of about 100 times more precise than it originally had been. So if you've ever had LASIK surgery before, you've actually had a little bit of help from Hubble and fixing Hubble as well. So again, one of those great things that often it doesn't seem like something that would affect us here on Earth, putting a telescope into space, but we end up getting a tremendous amount of technology just out of these things here. Now, in the 90s, the late 90s and the early aughts, we really, with ground-based telescopes, started to catch up with Hubble, mostly because we would fire lasers at Hubble to blind it during its time. And I'm just kidding about that. It kind of does look like the Death Star firing twice at the same time there, right? But these are lasers that are actually being shot into the upper atmosphere, where they are heating up the molecules that are up there. And then we have a camera that actually looks at those glowing molecules and is able to figure out just how light is bending as it comes through our atmosphere. And then we are able to deform our mirror to smooth out the light as it comes through. Because looking through our atmosphere is like standing at the bottom of a pool and looking out and attempting to figure out what all those shapes and things are out there. It really messes with the sharpness and the precision of what we're trying to see. So to give you an idea of what this is, which we call it adaptive optics, we have little, mechanisms that will just ever so gently move these mirrors, oftentimes, maybe about a couple of times the width of a human hair, multiple times per second, and just very, very carefully smooth out the light as best that we can as it comes in. And this ends up giving us some absolutely amazing imagery. And I really like this. Take a look at this. That's looking at the mirror as it's doing observations. And I love that the mirror is that's like not like heat or anything you're looking through. That's the surface of the mirror deforming in real time as it's taking an observation of something in the sky. But to give you an idea of what adaptive optics does for us, you can see this is some terrible seeing. There is several objects there, but I don't think we can even tell that there's one. But if you turn the adaptive optics on, boom, there they are right there. Exactly where they're at. Two stars right next to each other. Perfect. Then, great one. This is the sun, looking at a sunspot. This is regular without adaptive optics, but let's turn it on. Boom. There you go. Now we're just looking at a little bit from the Earth's atmosphere, sort of wiggling the image there, but there's really not much that we can do about some of that. But again, we're back to that light problem, right? Because here on the surface of the Earth, there are only certain wavelengths of light that we can actually observe. Our atmosphere blocks some of the wavelengths of light, right? Like ultraviolet radiation, it's very good at blocking that. For the most part, we still oftentimes have to put a little extra block when we go out in the sun, right? For that, but still, it blocks a good amount of that. Infrared, the water vapor in the Earth's atmosphere actually blocks most of the infrared. NASA just retired a telescope called SOFIA, which was a infrared telescope in the back of a 747 where they would fly it above at very high altitude, above most of the water vapor, so they could actually do infrared astronomy out of it. But Webb, the James Webb Space Telescope, we're looking primarily in the infrared here. So red to near infrared into the infrared itself. So to kind of just run down the numbers with you a little bit on the differences between Hubble and Webb here. First of all, Hubble is about 2.4 meters in size, about 8 feet across. So maybe my span of my arms here is about the size of the primary mirror on Hubble. But with Webb, we've increased that to 6.5 meters. So significantly larger with that there. And to kind of give you an idea of just how big Webb is, there is a really great image of one of the technicians looking at the primary mirrors of Webb as they're inspecting it. He's up on that little genie crane right there. But I feel like this doesn't quite give you an idea of just how big it is. So here's two other technicians looking at the primary mirrors as well with this, and also sitting on the spacecraft bus or the body of the spacecraft down there as well. Now, one thing that we had to do with Webb, infrared telescopes, if you want to look at something in the infrared, your telescope actually has to be colder than what you want to look at. And I know that sounds really weird, right? So if I had an infrared, camera, the chip, the CCD for that camera would actually need to be colder than the objects I'm looking at. And that's very interesting because they generate a lot of heat in order to do that, right? So with Webb, we had a little bit of a problem because we wanted to make Webb as cold as possible. And with our normal ability to cool things, we weren't going to actually get as cold as we wanted to. We were only going to get down to about minus 370 degrees Fahrenheit, right? That's not cold enough, if you ask me, right? So I still wearing shorts at that point, right? So, but we wanted to make it even colder. We wanted to take it down to almost minus 435 degrees Fahrenheit. So just, about somewhere in the order of 24, 25 degrees above absolute zero, which is, you can't get any colder than that. Physics says no. So we Northrop Grumman built this incredible sun shield in order to help block as much radiation as possible from the James Webb Space Telescope. And these pieces right here of Kapton are ultra thin. They're maybe just a couple widths of a human hair thick. And there are 5 of them, and they're roughly about the size of a tennis court. So yeah, they're very, very big. And this is actually one of the largest unfolding or folded and unfolding structures that we've ever made like this, at least in terms of what we can tell you with that speculation otherwise in other places, but that's not a talk for here today. So, so this one here, working with that, and this was very difficult to work with. During one of the deployments, there were some tears that occurred, and you can only tear so many before the radiation will be able to get through, and it will not allow the Webb to get as cold as we want it to. So we really, really needed it to work, and Northrop Grumman and NASA really put the effort in to make sure that it was going to work. And that was very, very important, because there was another aspect about the James Webb Space Telescope, which is that something the size of a tennis court, you cannot launch it when it's the size of a tennis court. So I don't know if anybody knows that, but no, you really can't do that. Really, one of the biggest things you could launch a payload on back in the day was the space shuttle. And Hubble was about as big as it almost basically filled out the entire payload bay of a space shuttle. So, and those are, 60 feet long, 10, almost 12 feet wide and almost 15 feet deep. So, I mean, that's a bus. That's a bus. And even then, that was right on the edge of what we could do. So here we are now. We've got a, we've got a tennis court. And oh, by the way, we've also got something that's like 20 feet long as well. So how are we going to do this? Well, we had to basically figure out a way to fold it all up and work with it that way. This is what it would look like fully deployed. So this is actually what Webb looks like right now. Although it is most certainly not in this simulator. It's out in space about 1 million miles away from the Earth. But Webb, we were talking about looking in infrared, right? So what does that mean? We were talking a little bit earlier about infrared and different types of light and what it should look like. Well, Hubble did actually have an infrared instrument for a while on it. And this is the Pillars of Creation in the Eagle Nebula. And this is imaged by a visible light instrument on Hubble and then an infrared instrument on Hubble. And one thing that you'll notice is that in visible light, we see that there is a lot of gas and dust, and we don't really see a lot of stars there, right? It's really difficult for us to catch that. But over here in the infrared, we actually see oh no, there's a lot of stars there, significantly more than you would think if you were just looking at the visible. And oh, by the way, there are stars inside of this here as well. So I always like to do a little demonstration with our infrared camera at Griffith Observatory, where I'll cover my hand in a trash bag and I'll ask people, how many fingers am I holding up? And they usually can't guess it. But then I'll go over to the infrared camera and it'll cut right through the trash bag and show how many fingers I'm holding up on my hand. Because that's what infrared does. It cuts right through the gas and the dust and shows us exactly what's there at those wavelengths. And that's very, very handy to have. And also another thing too, is that as we look further back into the universe, we are looking at bigger and bigger redshift as there's faster and faster expansion from our perspective. So that means that there's actually only so far Hubble can look back. It is limited because it can only go so far into the red wavelengths. However, with James Webb, we can go even deeper. We can go redder than red, right? That's really a bad way, honestly, to describe infrared, redder than red. But bear with me here, because we could possibly go deep, deep, deep far back to possibly seeing galaxies 200 million years after the Big Bang. I mean, we're even, at that point, we may even be talking about some of the first stars to be made in our universe. And that would be stunning if we were able to see something like that. With Hubble, they never expected Hubble to look back as far as it could. So I think that's boding well for Webb, that already in the first picture, we think we're finding things further back than Hubble can look at all. And we've got hopefully a lot of years ahead of us with Webb to optimize it and really massage the data and work with computers here on the ground to maybe look even further back than our wildest dreams could possibly conceive. So we've got this big telescope, right? We folded it up, but there's a problem. There's Still not many rockets that can actually fit this. Oh, yeah, actually turns out there's only one. And that's the Ariane 5 that is launched by Arianespace, which is a consortium of European companies that also work with the European Space Agency. And there was a bit of a trade where we said, we'll give you some instruments on Webb if you give us a launch. And they were like, let's do it. So the hands were shook and the ink was dried on that one. And we were able to launch on it there. Now, here's the configuration we had to put Webb in order to do it. You're probably asking yourself, well, where's the sunshade in it? Oh, there it is on the back right there. There's our mirror. We folded our mirror backwards a little bit, and also that big boom there to hold our secondary mirror. We had to fold it up and over itself as well. And all the systems on the spacecraft bus, like our comms dish and our radiators and our solar panel, we had to fold that up as well. So, and there's a lot of folding going on, and it was a lot of origami, I guess, if you want to look at it that way. But of course, it was very expensive origami because that is one thing that I guess we really can't get around without talking about, which is that Webb was expensive. It was roughly somewhere on the order of about $9 to $10 billion with that. That's a flagship mission for you, though. It can do that. But I think with some of the things that we're already seeing from it, it's pretty well spent with that there. With that. So, fun thing. Okay, so we were done assembling Webb, which, by the way, I completely forgot to tell you all. Webb was assembled down in El Segundo at Northrop Grumman there. So, this window on our universe was made not far away from us here up in Pasadena. And they had to ship it by boat, and it had to go through the Panama Canal in order to get to the launch site in Kourou, which is in South America in French Guiana. It was an interesting process because nobody really actually knew, except for the people working on the Webb team, when Webb left the port of Los Angeles. Because it left you kind of left, without telling anybody. And it ended up in the Panama Canal and everybody saw it there. But then after that, it left without telling anybody as well. And then eventually it arrived in French Guiana. And they did that because they didn't want pirates to actually try to commandeer the vehicle and hold it for ransom. Like, I'm not even kidding about that. They did not tell anybody when Webb was being moved. They told us when it was done being assembled, but they didn't tell anybody when it was being moved because they didn't want anybody to know when it was being moved. Or I guess they didn't want the wrong people to know when it was being moved. But yeah, it eventually arrived there, and there was some tests that you have to do, what we call integration. So basically making sure everything works together. You see these folks wearing these sort of spacesuit looking kind of, fit on them there. This is during fueling, so we're putting the fuel that its thrusters use, hydrazine, in there. Hydrazine is very toxic. It will kill you very quickly. As the saying goes, it smells like fish, but nobody's lived long enough to confirm it. So that's why they're in those positive pressure suits. They're basically in literal spacesuits to make sure that if a hydrazine leak were to happen, they would be safe. Luckily, didn't have a leak or anything like that. And we continued integration, eventually putting it into the payload fairing of our Ariane 5 rocket. And then we rolled the Ariane 5 out onto our launch day, which of course, the universe is always really great at making the physics for us to have to launch on certain days because this went on Christmas morning. So, right, what a great little present for us. Except for here on the West Coast, it was like 4 a.m, Christmas morning. But some of us got up and we watched it happen live. So here's some of the footage from the launch. So with an Ariane 5, we have our main rocket on the first stage fire up, and then the 2 solid rocket motors on the side will ignite, and then we are on our way, and boy, I hope it works, because that's $10 billion flying right there. So essentially, the most expensive single object anyone has ever made is now riding a big column of fire up to very high velocities, somewhere on the order of 22 to 23,000 miles per hour. So no big, right? Luckily, everything went exactly as planned. The injection maneuver that the Ariane 5 did was actually more accurate than it needed to be. This was a very big moment here with the payload fairing coming off. There had been some worry that with the payload fairing coming off, the pressure the pressure release during that may have actually, possibly torn the sun shield, but it didn't. So we're all good about that. And then we watched the upper stage deploy James Webb, and that was it. This was the last time human eyes would see it as it is, because it is now on a journey to 1 million miles away from the Earth. That's it. We're never going to see it again. We're never going to go get it again. It's not like Hubble, which was designed to allow people to actually come up to it and fix it and service it and add new instruments. Webb is one and done. That's it. If something goes wrong, it's broken. And there were 387 single points of failure during deployment. So for 30 days, there were 387 times that something could have gone wrong and there would have been no way to save Webb. So for most people, when they think of deploying their satellite, they say, we're done, but not us. No, we still had a month to go. So a full month of terror. It's like at JPL with landing on Mars, they called it the 7 minutes of terror because 7 minutes from the top of the atmosphere to landing. Well, I proposed the 30 days of horrifying origami, but nobody picked up on that, unfortunately. But there's our solar panel deploying, which was something that needed to happen very quickly after deployment. So that was fantastic to see that, and all breathed a little sigh of relief. And now comes to the hard part, which is that we're going to be heading out very far away to what we call a Lagrangian point, or L2. That is an area where the gravitational influence of the sun and the Earth balance each other out. So you can actually drop an object in there and it will stay mostly in that area. It makes this really cool orbit that we call a halo orbit. So there will be a point that it just kind of goes around as it stays behind the Earth. And we wanted to keep it there because that point, there's a little less radiation actually there. So we could make Webb even colder by putting it at L2, right? So, not much colder, but hey, we'll take a degree or two, right? That'll work for us. And there were some things that had to happen on the way out there. So here comes the origami. Everybody ready for it? So, all right, here we go. All right. So we shall now commence unfolding. So we saw the solar array deployment. We're now deploying our high gain antenna. We had to fire our thrusters to get ourselves sort of lined up. We actually ended up not having to do as many burns, which means we have more fuel, which means we can have Webb last longer. So great. Thank you, Ariane 5 at Ariane Space. All right, so now we're going to get ourselves into the proper position, and now we're deploying our forward system. And now we're going to pitch backwards a little bit because we need to make sure that we're in balance to also deploy the aft system that's going to unroll. All right, now our telescope array is actually lifting itself up a couple feet, and now we pop the covers off of the membrane for the sun shield there. And now we pop some more of these. Okay, now we're pulling our sun shield out. Please don't rip. Okay, now we're going to pull the other sun shield out. Please don't rip. Okay, we're good. All right, now we're going to tension the sun shield so that all 5 sections are apart from each other. Please don't rip or stick to each other. Okay, now we're going to deploy this flap, which we can actually use the pressure of light from the sun to kind of stabilize a little bit. Now we're deploying the radiator so we could start to cool down a little bit more. All right, now we're releasing some of the systems so that our radiators can fully deploy in just a little bit here. All right, now we're going to pull out our secondary, and now we're going to pull that boom all the way out. Okay, that looks good. Okay, we're going to deploy one side of the mirror, and we're going to deploy another side of the mirror. And there you go, done. 30 days in a minute and a half. And everything had to go right? And guess what? It did. So, boy, were we very happy to find out about that. There were no tears. As far as we could tell, there's no tears in the sun shield. No part of the sun shield that's even too close or too far from each other. They're just right exactly where we want them at. So we were going to take our first images with it. And we were all very excited to see those images. You guys want to see them? Okay, here they are. So, and I'm sure you're probably saying, well, what's going on here? Well, first of all, we had to take a selfie when you get out there, right? You're a million miles away from the Earth. You got to take a selfie. It's just the way it goes. But also, we looked at a specific star, and we wanted to make sure that our secondary mirror was actually reflecting light onto our primary mirrors, and then also that the primary mirrors were reflecting light onto the instrument. So that told us that everything was working as it should. And then we started to very carefully dial in these mirrors, because each segment has a small motor behind it so that we can move it as essentially precisely as physics will allow us to have that light meet at the secondary to go into our instruments. So we ended up, taking another, just to kind of show you the difference between the selfie when we first took that photo, and then finally with everything lined up with the light from that star, just, spot on exactly what we wanted to see. And then we also started to take images with our instruments to make sure that they were as sharp as they needed to be. And also our fine guidance sensor as well, which is used to precisely aim Webb and keep its body where it needs to be, especially to make sure that the sun is blocked no matter which position Webb is looking at that moment. And actually, very interestingly, the fine guidance sensors, their resolution is so precise, it's so crisp that they're going to be able to do science just by the systems that keep the telescope pointed in the right direction. So again, this is like bonus round with everything that we've got going here. By the way, this is a little website right here if you want to take a quick photo of it, if you want to know the current status of Webb. I checked out a couple hours ago just to make sure that everything was going fine in case I needed to call NASA and tell them anything. And as you can see right now, the coldest instrument called MIRI on there is running at a nice balmy minus 449 degrees Fahrenheit, or about 6 degrees Celsius above absolute zero. So, or about roughly 10 degrees Fahrenheit above absolute zero. So, yeah, it's a little cold. By the way, the side that has the sun shield is at 122 degrees Fahrenheit. So there's almost a 570 degree difference from one side of Webb to the other. And it has to work like that. And it has to work in that kind of a configuration for at least a decade. So that's tough, right? Keeping a tennis court at minus 449 Fahrenheit for a decade. So that's why we made sure to make sure it would work. So feel free to check in, make sure Webb's doing what it's supposed to do. If not, there's numbers you can call, I'm sure. So now we can get into the real meat and potatoes and actually take a look at everything that Webb is looking at. You guys want to see some of the images? Okay, let's take a look. So this is one of my favorite ones right out of the gate, which is called Stephan's Quintet. So these are multiple galaxies that are interacting gravitationally with each other. And when you see them through a telescope, they look like galaxies. They are these beautiful spirals of gas and dust. But in Webb, we don't really see those beautiful spirals because we're looking through the gas and the dust and we're seeing areas that have very high energy. So we're seeing where places are interacting with each other. And from that, we can learn things like the evolution of stars in that area, cosmology, chemistry and other things, all in those areas. And by the way, it's not just this specific wavelength we look at. We actually look at different wavelengths of infrared as well. Now, this is not the colors that it would look like in infrared, because I can't really describe infrared to you because, you can't see infrared, right? It's like asking somebody to say, hey, what color is blue? It's like, I don't know, I can't tell you. So when we put these colors on things, this is not like the actual colors that we're looking at, but these are essentially colors that are used to help us approximate and get things across. So we could see that there are certain gases interacting with each other that change the composition. So we go from this area where we've got lots of blue, which I believe is oxygen in that area, to green where there's lots of carbon in this image right here. So quite a lot going on there. By the way, Webb is going to be capable of looking at objects from about Jupiter out in our own solar system, and that's great because we have not sent many probes out to our outer solar system. Uranus has not had one since Voyager 2 in 1986, and Neptune has not had one since Voyager 2 in 1989. So there's not much we actually really know about them. Most of it is based on what we could see with Hubble, which was right at its limits in our own solar system. And ground-based observatories, which are not the best, right? So, and sometimes the data look contradictory to what Voyager gave us because we're not there, you know? But with Webb, we're going to definitely be able to do that. So, really great view of Jupiter here. Then we can actually see the different cloud bands in there, which tell us different composition, different temperatures. Also, really need to note here that this is not like pieces of Jupiter coming off. Those are actually the aurorae that happen on Jupiter. Jupiter has a very powerful magnetic field. So much like the Earth's magnetic field that funnels charged particles from the solar wind down, and they interact with our atmosphere and they make the beautiful aurorae in the north and south poles here at the Earth. Jupiter has the exact same thing as well. Although its aurorae are like Earth's across. So I can only imagine what they must look like. It must be spectacular. This was another great one just to kind of show off the sharpness that we were getting from Webb with this here. And just to kind of annotate this a little bit, again, we're getting the aurorae. We're literally seeing the aurorae so well that it's generating diffraction, or it's like spreading the light out. In that we can actually see rings around Jupiter, which many people don't know. Jupiter has rings. Jupiter, Uranus, and Neptune have rings. So all the 4 outer planets have rings. Saturn's are easy to see because it is made mostly out of water ice. So imagine snow, very reflective of sunlight, right? Well, Jupiter, Uranus, and Neptune, those rings are made out of dust primarily, and dust really doesn't reflect a lot of light, right? So our eyes can't really see it at all, but in the infrared, we can absolutely see them. So, and also we've got a couple more of Jupiter's small moons, and I'm talking really itty bitty here, maybe a couple 100 miles across, and we're looking at this from, 500 million miles away. So no big deal. This is a really great one that I liked right here, M74, a spiral galaxy. And again, cutting right through all of that dust and gas and being able to see the structure that is in there. And that's just absolutely astonishing with that there. This is one that just came out a couple weeks ago from the Tarantula Nebula. So I don't see the tarantula, unfortunately, but it's there apparently. But this is a nebula in one of the Magellanic Clouds, one of our neighbors that we have. Also, we think detected one of the coldest places in space, so a great place to aim a cold telescope at. This is the Cartwheel Galaxy with some other galaxies around it. It interacted with those galaxies and it ended up making this ring of material around them there. And I absolutely love this image because, that's a star from the Milky Way. That's a star from the Milky Way. Everything else is a galaxy. So, that is amazing to have this kind of resolution with this happening right here. It's just astounding. And then, of course, other instruments see different things. So we'll see much higher energy interactions happening here, which tells us about the evolution of space in that area. So absolutely amazing. And then combine those two instruments together, and this is what we get out of that. So beautiful with that there. Anybody know what planet this is? It's not Saturn, not Uranus. Neptune, yeah. It's like we're going to go out consecutively. So this was Neptune, snapped by the Webb just a couple months ago. So we could see the rings. We could actually see that you could see some of Neptune's moons as well out there. And we could also see this really bright object right here is Triton, which is Neptune's largest moon, which is bigger than Pluto. So it's a massive, massive moon. So very, very excited that we could study it in that kind of detail. And then just a nice close-up of Neptune here. And I'm just going to go back and see if I see any galaxies right out of it. Yeah, there's a couple galaxies up there, so no big deal. All right, this is the Carina Nebula. This is a star at the end of its life. This is what our sun is going to do at the end of its life. It'll basically blow off its outer layers and seed the next generation of stars in our neighborhood. So, very, very beautiful with that there. This is also Carina Nebula. Look at that. So just the detail that we're able to get, and especially because we're looking, a lot of these stars we're looking through the dust there. So amazing stuff. All right, so this is Hubble, right? This is Hubble's view of the pillars of creation, and this is Webb's view of the pillars of creation. So this one just came out a couple days ago. So this is about as fresh as it gets with what we've got here. And then just to kind of give a really good comparison with what we're going to be getting from Webb, this is a Hubble image of the first deep field that Webb took. So you can see it's not bad. It's pretty good. We could see that there's some of these streaks right here. And what that is that there's a galaxy that has a lot of mass in this area. It's made out of a lot of stuff. So its gravity is actually warping light and smearing out the light from objects behind it. So you can imagine bending light because the gravity is so strong. That's what it's doing. And here is what Webb was able to see in the same area. So that's the difference. This was about 20 days of observation, roughly. This was about 8 days with Webb. So again, infrared and bigger means that we're looking at bigger areas and we can take in more light, which means we can not look at things any longer than we need to, which means we can look at even more things with it there. And I'm just amazed by this image because there's already, after this image was released in July, by the end of the week, there were already 6 to 7 papers from astrophysicists who were attempting to determine whether certain objects that we're seeing here were already breaking Hubble's records in terms of objects that we could see in distance. So we'll have to see. That kind of stuff takes time to confirm, but a few of them are looking good. And knowing that happened in the first image the first deep field that Webb took, that's pretty spectacular, I gotta say. And then just a really nice close-up of that field here, and you can see that gravity just bending the light of those galaxies there. It's just amazing. Physics is wild. So, right? So with Webb, it's a great start. Everything's looking fantastic. It's running exactly like we want it to. And it's already giving us amazing imagery beyond what we even thought it would be capable of. So really looking forward to the next decade with Webb. And hopefully I'll be able to come back maybe like next year or something, bring some more results, talk about some cool things. And I want to thank you all for listening to me talk about Webb today. And if you have any questions, I will be happy to take them. But thanks again for listening. Thanks for coming on a journey across the universe with me.